Okay, Mr. Hunt here. We're doing higher order derivatives and rates of change. Just as we can find a derivative of a function, so we have f of x, well, I can find the derivative, but I can also find the derivative of the derivative. So I could take this one, whatever function that is, find the derivative, and we say that's the second derivative, and we write a second prime there. We could carry that on and keep going and do the derivative of that, and we get the third derivative, f triple prime x. And after that, look at the chart. I'm on page 11. You can see the chart. After that, we actually go to numbers. We don't often get to that in this class very much, but we'd write the number after the fourth. That means the fourth derivative. This works the same way with y, so like this would be y double prime. The other one that's important, Leibniz notation, you can see on the very right there. He was a mathematician, Leibniz, and he wrote it as, this is dy dx, we've seen that. That's a derivative of y, so we have a function like y equals 2x. Derivative of y with respect to x, the variable. And it could be a different variable, this one on bottom, whatever variable you're doing in respect to, maybe instead of y equals 2x, y equals 2z, so we would change this to like dy dz. The derivative of y with respect to the variable z. But what's important to note for him in his notation, he then said the second derivative, d squared y dx squared. So this part, the d squared, that's the second derivative of this variable y with respect to the variable x. So it's just another way of saying the second derivative. And you can see carrying it on, it still goes further than that. But the farthest we'll see is we'll see something like this. So now that we have that, let's look at the example. Here's f of x, 2x cubed minus 4x squared plus 7x minus 8. And so it says find all of the derivatives of this function, all of them. We're going to go to infinity. So the first derivative, I'm just doing the power rule for a couple of these. 6x squared minus 8x plus 7, and then plus 0 for the derivative of negative 8 is 0. I'm going to keep going, so we're going to get them all. You're going to see what happens, though. Next one, 12x with the power rule. Negative 8, derivative of negative 8x, and the derivative of 7 is 0. F triple prime of x is 12, and then 0, right? So just 12. And then the fourth root of x, derivative of 12 is 0. And then if I want to do the fifth derivative of 0 is 0. And then the derivative of 0 is 0. And so you can see after, let's see, the fourth root and on, the derivative is just 0. So you can make a note of that. I put on my paper, all derivatives after the fourth root and on are 0. So we found them all. They eventually, so this demonstrates a polynomial will always terminate in the eventual derivative being 0. Only for polynomials that works. Let's do one more. The next example, I have f of z equals 1 over z. Find the first 5 derivatives. So I'm going to do f prime. Now, I could do, I'm just going to write QR, quotient rule. That would work. But for this one, because I'm going to have to do it 5 times, the easier way is to change my original function to z to the negative 1 power. That was really the first power on bottom, move it up as a negative exponent. Then I just have to do the power rule. So the first derivative, negative z, I brought that negative 1 down in front, to negative 2. I'm going to change all these negative exponents at the end. But I'm just going to do the power rule several times in a row here. Second derivative, bring the negative 2 down, positive 2 now, z to the negative 3. F triple prime of z, do it again, negative 6, z to the negative 4. I should have written fourth derivative of z with respect to z. 24z to the negative 5, and then the fifth one, negative 120, z to the negative 6. There's the first 5 derivatives. That's correct. I'm just going to say always write your final answers with positive exponents. So I'm just going to go back and change them all. First one, there's a negative 1. That's this 1 over z squared. Let's just put that on bottom. The next one, the 2 is still in the numerator. The z cubed is now on bottom. The next one, negative 6, and then z to the 4th over z to the 4th. The next one, 24 over z to the 5th. And then the final one, negative 120 over z to the 6th. So you can see each one, if we start and we look up here, 1 over z, it became, the sign changes every time, negative, positive, negative, positive. And it goes up 1 degree on bottom. And you multiply by the exponent, like here, to get to the next one. We actually multiply by negative 3 to get there. Multiply by this to get 24. So a little pattern to it, but there's the first 5 derivatives. Okay, and then the last thing we do today is just one example as we start to look at applications. So I say at the bottom of page 11, we started looking at rates of change in this unit, average and instantaneous. This became the derivative of the function, the instantaneous rate of change. And what we're now going to do in this unit to finish, and then several other units coming forward, we're going to end with applications in every unit, which one is just, they're awesome to see how we use it. And the second thing is just, it's good to know really real life, not just in math, but how we can use these things. So we'll look at several different examples here of, whenever I say rates of change from now on, that means instantaneous rates of change. I'll specifically say average rate of change if I want that one. But we're going to look at rates of change. We're going to look at how it applies to different shapes, parabolic motion. You might have done that in physics. At the end, we might have time to do some economics problems, falling body problems, and then really one of the most important, position versus velocity and acceleration. So we'll look at those. Okay, so I'm just going to finish with one example on page 12 and the 3 parts there. So it says, I'm just going to put example. This is A. Find the rate of change of the volume V of a sphere with respect to its radius. So you just got to imagine you have a sphere, and the size of the sphere is based on the radius. So you have a big radius, bigger sphere, smaller radius, smaller sphere. So the rate of change of this is saying, well, what if this sphere, let's say it sort of starts like that, what if the radius r is increasing? Let's see if I can write that. Oh, increase, well, that's all I can get to. What if the radius is increasing, then you'll get a bigger and a bigger sphere. And what's the rate of change of the volume? Okay, so how much volume is there based on where the radius is at? So based on how it's changing. So if we do the derivative, so before it was instantaneous rate of change, that's the derivative. So in application problems, it'll be, so we're doing the volume of a sphere, it'll be the rate of change of the volume. So how fast the volume is changing at a certain radius. So I need the volume formula. I know you all remember that from geometry. 4/3 pi r cubed. So we're going to do the, I really should have written this. We're doing the volume in respect to our variable, which is the radius. I should do v of r. That's the variable we're doing this in respect to. So part A, find the rate of change of the volume. Just basically find the derivative. And so notice that these are all coefficients. They're all numbers, 4/3 and pi. So I don't have to do product rule here. The constant multiple rule says, okay, I just take those out front. Then I do the power rule with r cubed. So the derivative of that is 3r squared. And I can simplify that. Notice that the 3's cancel, or you could have done 4 times 3 is 12, and then 12 divided by 3 is 4. So I get 4 pi r squared. What's interesting is that is the volume of the sphere up here. if you do the derivative, this is actually the formula for the surface area of the sphere, which is interesting. So then part B asks us, okay, this is the derivative, the rate of change of the volume at any radius. So part B, just find the rate of change of the volume at certain radii. So part B just says, well, when the radius is 5, what is happening with the volume? So I'm really doing this, V prime of 5. And so I'm just plugging 5 in for R. Order of operations, I do that first. That's 25 for 5 squared. At times 4, I get 100 pi. And similar for V prime of 10, the rate of change at 10, 4 pi, 10 squared. That 10 squared is 100, times 4 is 400 pi. And if we wanted a decimal version, we could put those in to our calculator. And finally, the last part on C there, I'm going to try and squeeze it in at the bottom. The radius, they say, okay, well, we didn't have any units before. Now they're saying, all right, well, what if the units for the volume were in cubic centimeters? Put this up top, cubic centimeters, and the radius is just in centimeters. What would be the units that would be appropriate for this? So really, it's for volume, it would be the cubic centimeters of volume. I'll just put like this. Here's how I wrote it on my sheet here. So per centimeters of radius. So we're finding the rate of change, okay, the volume, which is in cubic centimeters, per the amount of radius of the amount of centimeters of the radius. All right, that's where I'm going to stop for today. I'll pick up with the next example and a lot of really fun applications moving forward.